And I thank you, David, a lot too for introducing me and for inviting me to this seminar. It's not the most usual that I speak about seminar about theoretical neuroscience, but I mean, okay, I mean, the way I will start, hopefully it will kind of make sense that there are many connections. So let me start. My first slide is basically just very small selection of some of these papers coming from statistical physics that kind of pioneered this field of using statistical physics to study neural networks. And you know them, at least the first one, you know, and probably the second and third as well, at least some of you. And I mean, why are we in the seminar of theoretical neuroscience? I think partially because a lot of these early pioneers of the field then moved into theoretical neuroscience. And some others didn't, and maybe kind of kept the field of applying statistical physics to the artificial neural networks a bit dormant for some decade or more. And you know, just some more of the history. Just a few slides. Like another slide that I like to show is this school in Lezuš. Lezuš is a place that I absolutely adore. And you were mentioning the mid 80s. So this is from 85. And you see, I highlighted here some of the names that are, you know, Mark Mezar, my PhD supervisor, Vera Sorot, are kind of close to me, John Hopfield, who is kind of the pioneer of all this. But you see, for instance, the name of Jan Lecan. And I really like his story about this conference. He says that, you know, back then when he was kind of brainstorming how to cook up the convolutional neural nets, people in computer science or say engineering would barely listen to him, but the physicists kind of paid attention. So that friendship kind of started very early on. And here, probably there are students in the audience. So if you want to kind of read some textbook where 4 of my kind of favorite ones, not very recent ones, but very, very nicely kind of written on this field would be these ones. And of course, this kind of general introduction these days cannot go without the mention of Giorgio Parisi, who stands behind a lot of the techniques that are used in this field. And the applications of these techniques to machine learning were even mentioned by the Nobel Committee in this little paragraph that I give here. So that's a few slides about this kind of studies that started a long time ago. And these days, when we hear deep learning, I am in computer science, but also in physics and in the physics department, in basically all sciences, many people are so excited about deep learning among, you know, so here I gave some like applications that I really enjoy hearing from colleagues in EPFL. These are some of the things that colleagues here at EPFL developed. I guess being in a neuroscience seminar, the Deep Lab CAT developed by Mackenzie and Alex Mattis is maybe closest to some of you. So all these are amazing achievements that probably 15 years ago we could have only dreamed about. So that's what's going on, and I could go on for long giving you more examples. But where I want to go rather, and why cannot I go forward? Oh, okay, it's just slow. Where I want to go rather is to make a point that despite all this kind of engineering progress and amazing science and amazing performances, we are quite kind of mitigated in terms of understanding what's actually going on. So again, I could talk for long about all the kind of theoretical questions underlying deep learning, but I will stick to one because I think that's one of the most basic ones. And if we kind of answer well this one, then hopefully a lot of the others will follow. And the basic questions is how many training samples are actually needed for a given task? And here on this slide, I just give you the usual snapshot of this CIFAR-10 dataset that a lot of papers are using to kind of benchmark their methods, or at least in the past have been. And this dataset has 10 classes and 5,000 samples per class. And such a basic questions, you know, people compete on this database for what is the best performance, which algorithm and architecture gets the best performance, but we actually do not know whether that is close to optimal, or how many samples do we actually need information theoretically to achieve a given performance. And if the current methods are not yet at this information theoretic minimum, well, how to do to actually get there? So this is, to me, this is very frustrating. That's such a basic question. We don't have a mathematically, not even mathematically, like scientifically satisfying answer. So this talk, I want you to think of these two questions. What is the best information theoretical achievable test error on a given task? And what is the best efficiently achievable test error on that task? And you could say, oh, wait, hold, that's the same question. No, that's not the same question, right? The difference is important. The first question is about statistics, about is something possible? And the second question, is it possible fast? Is it possible with an algorithm that actually does not run exponentially slowly, say in the dimension or in the number of neurons? So this distinction between what is possible statistically and what is possible computationally is very important. And for me, it's kind of at the core of the theoretical questions about deep learning. So this is not the same question. Okay, so now I want to go back to the statistical physics and these results from decades ago, and kind of walk you through how actually statistical physics approaches this question of sample complexity. Because as I told you, in general, we don't have an answer. So in general, we don't know. But what can we do to at least provide answer in some restricted setting? So that's what actually goes back to the papers that I showed you. And in particularly this one by Gardner and Derrida, called the 3 unfinished works on the optimal storage capacity of networks. It says that's on the storage capacity, but on the way, they actually also introduced this teacher-student perceptron, which is a framework in which I like to think about this optimal sample complexity question. And that works the following way. You take the data X, and you have a teacher network that generates some weights W star, and that network generates the labels Y. So the labels do not come from some application. They are being generated by this artificial teacher network that in this paper, for instance, takes this form. And then you have a student neural network, and the goal of the student neural network is the usual one, as in supervised machine learning, is the one of recovering the function that maps inputs to the outputs, the X to the Y's. So that's the problem that they studied there. And this, of course, can be, so in the paper I showed, this was studied without the hidden units. This teacher-student setting is, of course, straightforwardly generalized to the feed-forward multi-layer networks, as I kind of say here. So you take input data. Those can come from some application. There are n samples of d-dimensional data. Then you generate weights, W star, and you use a neural network, the teacher, to generate the labels. And then the student observes the pairs. And for simplicity, the architecture of the network that can only make things simpler, not harder. And the goal of the student is to learn the function from X to Y. So here I already put aside some of the difficulties, such as what is actually the function. So here I know the function, and I can at least formally write what would be needed to do to actually answer the question of what is the optimal sample complexity here. And that answer is given by the base formula. One needs to write the posterior probability distribution of what were actually the weights that the teacher used. Those are not given to the student. Given what the student has, that's the observations of the outputs and inputs X and Y. And the teacher took the weights from some prior distribution PW and then generated the sample in a way that corresponds, this function phi here corresponds to the function that the neural network represents. And then the optimal way to actually get the best possible test error is to take the function and average the weights over that posterior. So at least in principle, we know what needs to be done. Then there are still troubles. One trouble is that this average is not tractable in general. So this is not answering the can it be done computationally efficiently question. Just let me make a remark here, because when one shows this Bayesian posterior, usually that's not what we usually do in machine learning. What we usually do in machine learning is, in computer science terms, the empirical risk minimization. We usually postulate some loss function L that compares the known labels to the outputs of the neural network, maybe with some regularization, weight decay, and then we minimize over the weights. And this loss function is one of your favorite loss functions. Whereas the Bayesian estimation that samples the posterior and averages over the weights that are sampled from the posterior is something else. Is in general algorithmically harder, but also gives you the optimal error for a given number of samples. So, okay, that's nice, but what is done next? Is this enough to make the problem solvable and tractable and we can write nice closed formulas? So this is not yet enough. We need to do more assumptions to actually make this a solvable model in which we can in detail write a formula that gives us the optimal error. And so here on this slide, I go back again to the paper of Gardner-Derrida and summarize here the additional modeling assumptions that they do in the paper, and then we will do in the next few minutes. And there are 3 of them. The inputs X that the teacher uses to generate the labels are actually not arbitrary, coming from some real application, say images. They actually consider them to be random IID Gaussian vectors. So big simplification. This is not that they assume that real data look like that, but under this assumption, they will be able to solve the question we are interested in. The second assumption is about the prior that the teacher uses on the weights. Again, the teacher will use the components of the weights in the teacher network will be random IID from some distribution PWs, but it's a separable distribution. It's not they are not correlated. And then the third, in a sense, that's maybe not an assumption, but a regime, a limit in which then the problem becomes tractable, is what in statistical physics would be the proper thermodynamic limit. And in this context, it is the limit where the input dimension and the number of samples both go to infinity with a ratio that is fixed. And these would be, and in this case, there are also no hidden units. So under these kind of further simplifications, they actually wrote a closed formula for the optimal test error. And that's, then, okay, that was 30, 40 years ago. But here in this slide, I kind of summarize in a greater generality how such a formula looks like, and also what it has to do with the algorithmic achievability of that error or not. And that's kind of a one slide summarizing this paper that we wrote now 5 years ago. So we are still in this teacher-student setting, and under those assumptions that I stated on the previous slide. So notably the X that is random IID Gaussian and the prior on the weights that is separable. And then the kind of replica formulation can be wrapped into a theorem, and that we actually proved in this paper, or kind of a meta theorem that says that in the limit where the number of samples and dimension go to infinity with fixed ratio, we write a formula phi of m that we call the free energy. And that formula doesn't have anything high dimensional in there anymore. The m is just a scalar parameter. And that formula actually implies both the information theoretically achievable error, this MMSE here, and then an error that is achieved by a message passing algorithm that is actually conjectured to be optimal among the efficient algorithms. And it is simply so that the optimal error is given by the global maximum of this free entropy, and the algorithmic best achievable error is given by a local maximum that has the worst error. So that's kind of the statement of the meta theorem. Now you might be wondering, okay, what's actually this free energy? So the next 2 slides give you the formula. It's not particularly insightful if you haven't seen it before, but it's, it's the free entropy, as in statistical physics, the average over the data and the labels of the logarithm of the partition function. And it can be written in this form. It's a sum of three terms. One of the terms is kind of simple, and the other two, they actually nicely carry the message of how this is general, how the weights the teacher is using, this distribution PW can be anything you pick as long as it is separable. And this term depends on the distribution, and it's given by this kind of double Gaussian integral, or one Gaussian and one of random variable that is taken from this distribution. And then there is this other term that has in there this P out probability distribution that depended on the activation functions. So what is actually the activation function that the teacher was using to produce those labels? That's hidden in this P out. But you can really plug here anything, and this is kind of generalized formula for this generalized linear regression that includes the perceptron, but also many other cases. And I will give you some examples in a moment. Now, okay, if you're a physicist, you know that the free entropy is useful to get everything, but if you're, say, from machine learning or computer science, you don't. So you need a second part of the theorem that tells you that using that free entropy, one actually gets an analogous explicit formula for the test error. And that's the formula. So, okay, now these were probably the most technical slides of the talk. So now, you can forget about the formulas, but kind of go back to the two questions. What is the best achievable test error and what is efficiently achievable? So what does this theory imply? So here I can go back to the example that's from the paper of Gardner and Derrida, where they consider what's in physics called the spherical perceptron. That's the case where the prior on the teacher weights is just the Gaussian, and the activation that the teacher uses is just the sine function. And if you take the setting, then the x-axis here is the ratio between the number of samples and the dimension. And you have three sets of, one curve and two sets of points. The red curve is the optimum from the formula taken in the thermodynamic limit. The black points, that's the run of this approximate message passing algorithm, then in this case is supposed to lie on the line, which it does with some fluctuations because the system is not infinite, it's maybe 10,000 dimension. And the blue is the result of kind of a vanilla out of the box logistic regression that in this case is actually not so far. It's quite close, optimally regularized. And so if that was always the case, you would basically have that the out of the box methods are so close to optimal that would kind of be information, but it's not always the case. And the other example that goes to another kind of line of work that in the 90s was studied, and that's the case of the binary perceptron. So now the teacher will actually use weights that are binary. And the solution of that is given in this paper by Geza Georgi with the phase diagram in there. And I just replotted kind of my way, also including the performance of the approximate message passing algorithm. So once again, the only difference is that now the weights W star binary, and the student knows about that. The student has that information, but it doesn't know which ones are +1 and which ones are -1. So the optimal performance is given again by the red curve, and you see that there is a sharp jump to 0 test error. So if the student has more than, this is 1.245 times the dimension samples, it's statistically able to learn the function perfectly, 0 test error. But now if you run the algorithm, the approximate message passing algorithm, it actually lags a bit behind, and only at a point that is 1.493, it actually starts finding this perfect generalization. And for reasons that, that kind of are not yet completely clarified in theoretical computer science, but seems to stand, this algorithm is actually the optimal among the efficient algorithms. So that implies that there is this hard phase where something is statistically possible, but not efficiently possible. And for comparison, I still have the logistic regression here, that does not have the information that the weights are binary or is not using it, and so it's not picking this kind of interesting behavior. So that's maybe less surprising. You could say that's because it doesn't know the weights are binary. But wait for the next example, where it will be more striking. So a third example and last one in this set of examples is not one that you have probably seen in those papers from 30 years ago, that if it's somewhere I'm not aware of it. That's kind of a more, I really like this example. The only thing you change, it's like the spherical perceptron in the sense that you take the teacher weights Gaussian, but instead of using the sign function to produce the labels, you use an absolute value. So, okay, now it's a regression problem. Now it's not a classification problem anymore. If you did not use the absolute value, if you just observe directly the product, then this would really be linear regression and it would somehow all be trivial. But the absolute value you would think is not doing much, but it's actually doing, it's complicating the problem in a really interesting way. And why phase retrieval? I mean, this kind of application actually pops up when you do imaging with light, and then you observe actually the amplitude and not the phase. And so it's like losing the phase. It's like losing the sign in the real domain. So that's why I call it this way. And I plot again the same graph here. What is the best achievable test error as a function of the number of samples over the dimension? And now the weights are Gaussian, so nothing tricky about them being binary, but the outputs are given, the teacher uses the absolute value. And that's another way to induce this hard phase. So this time, okay, sorry, I changed the colors. This one, the orange is the optimal performance, and the blue is the theoretical prediction for what the algorithm should do, and red is the run of the algorithm. So you see that agrees. And you again have this little region that is the hard phase. And you say, okay, nice, there is this statistically possible but algorithmically difficult region. But in the next kind of minutes, I will kind of persuade you that, this is not just a little region of, say, 13% more samples that you need to take into, to be able to do something algorithmically. This actually has kind of a long-lived consequences for what's actually happening in the phase retrieval. But before doing that, I want to kind of end this overview part of what. So I have this way, kind of this triangle that I like to show. That's how I like to think, kind of how to go forward from what has been done in this line of work decades ago, and what needs to be done in order to kind of be able one day to say, okay, we understood what's going on in deep learning. And this triangle includes three sides that are the algorithm and the data and the architecture of the network. And in this kind of overview of the line of work from some time ago, I have showed you the case where the structure of the data is not there, right? Remember, the axis, the inputs, they are IID Gaussians, and the labels are produced by the teacher. And the architecture so far, we considered there were no hidden units even. And the algorithm was not the gradient descent or its variance that everybody uses these days, but this approximate message passing. But instead, we would kind of like to see realistically structured data and multiple wide layers and gradient descent based algorithms analyzed. And so kind of going from the blue to the green, that's how I kind of like to think of, say, most of my work in the past, say, 5-6 years. And so I will walk you through some of that, and we will start with the algorithmic side. So let's start with the algorithm. So that's where I go back to the phase retrieval. So this is exactly the slide that I showed you 2 minutes ago. But now, right, this algorithm here is based on the approximate message passing, but nobody in practical machine learning uses that. People use gradient descent for good reasons. But so let's now look in this model synthetic setting, what's actually happening with gradient descent. Is gradient descent as good as this approximate message passing or not? So first of all, I'm not changing anything about the model and about how the data are produced. And for that, the natural loss function would be this one, where I simply compare the square of the labels with the square of this product, because I kind of nicely tell to the student, look, the absolute value was used there. So then this is kind of the natural thing that you should compare. And I'm thinking of the gradient flow with some standard initialization. And then what are the tools that we can use here to actually analyze that? So one large class of tools that one can use is what's called the dynamical mean field theory that we have been developing to answer some of the current questions in here I cite some of our recent papers. But for what I want to tell you, I will not be so much needing the dynamical mean field theory. I will not be going to detail to that. I will just show you this picture that is simply numerically, you run the gradient descent on this phase retrieval problem. And you take the thermodynamic limit, the dimension is getting bigger and bigger, and the number of samples is getting bigger proportionally. And then you see the fraction of success of actually learning the function. As the size is bigger and bigger, it's actually getting worse. This is likely some logarithmic shift of the curve. And is definitely, if you remember, I have this axis here. If you remember, you needed just the number of samples that is 1 times the dimension for the problem to be information theoretically solvable. You needed 13% more for the approximate message passing to solve it. Now the previous picture tells you numerically you need at least 7 times more for the gradient descent actually to solve it. And there was this shift to even worse. And then here I cite some theoretical computer science results that put some large constant, but really large proofs on how many samples are actually needed. So for sure, there is a big gap between the gradient descent and the approximate message passing. And in this paper, we actually argued that existence of such a big gap between what the approximate message passing algorithm or the optimal algorithm manages to do and the gradient descent manages to do, that is actually closely linked to the existence of this hard phase. So even though this hard phase was actually really tiny, it has kind of a long stretch consequences to make the life harder for the gradient-based algorithms. And it's not only gradient descent, but also stochastic gradient descent, including the Langevin algorithm and the variance. This is kind of this is not particularly a paper about neural networks, but about this kind of generic property that the hard phase actually makes the sampling algorithms, hurdles to the sampling algorithms or optimization algorithms. So, okay, but how to close that gap, right? That was the question that I posed. Is there a way to close that gap? And the answer is somehow in the empirical observation of what's going on in deep learning these days. You all know that these networks that achieve state of the art, they have huge amount of parameters and often weighs more parameters than actually the number of samples on which they are trained. So they are hugely over parameterized. And that's fine. That doesn't overfit and they just get great performance. So now thinking as a physicist and as a kind of statistical physics is more Bayesian, say Bayesian, I will do something crazy. I will say, the data are still the same. They are produced by the teacher that has no hidden units and uses this absolute value matrix. This didn't change, but that now the way I actually want to learn that function, I will now actually use M hidden units. I will kind of mismatch the model with which I'm learning with the true model that I know is the true model that produced the data. I just don't know the vector W. So instead of learning one vector W, I will kind of over parameterize and I will be learning M vectors W and somehow think that that will do better or that will do something. So from a Bayesian point of view, this seems kind of crazy because we are really mismatching. I'll just put some light. We are really mismatching the model. This should just not work. We are adding degrees of freedom and thinking that we will still kind of find the function back. So the thing here is that this actually indeed does help. It does help the gradient descent. And for this particular problem of the phase retrieval, this is something that we managed to prove in this paper by my former student Stefano Manelli and a colleague in NYU, Eric van den Eyden, where we actually managed to prove that, I mean, okay, the proof is slightly weaker, but morally what we proved is that it's enough to have twice the dimension samples for the gradient descent on this over-parameterized loss to work. So if I go back to my axis here, pure gradient descent, non-over-parameterized, needed something like 7 times the dimension, maybe more. But if I over-parameterize sufficiently, the number of hidden units needs to be at least 1 bigger than the dimension, then I only need twice the dimension. I'm still not reaching the 1.13 of the approximate message passing, but I reduced the gap by a lot. Of course, I also on the way told you that the approximate message passing is kind of conjectured optimal among the efficient algorithms. So over-parameterization doesn't improve it, it cannot. There is quite a generic proof that simple kind of tweaks like that cannot improve the threshold. Something really very different would be needed to improve it. So to me, this is interesting because this is kind of putting a clear evidence on inseparability of these algorithm architecture and the data. I'm so far not so much touching the data, that it might be that we observe this over-parameterization just because we stubbornly keep using the gradient descent. For reasons, because it's very robust, it's very fast, so maybe not stubbornly, maybe for good reasons. But this suggests that if we were actually using some better algorithms, that we would not need maybe over-parameterized neural networks. That's of course a speculation, but a worthy to explore. So that was about the side of the algorithm. And now I want to go to the other 2 sides. One about the data, and I really want to get the one about the architecture. So now actually, I don't know whether I have time for both. Maybe David, how much time do you think I have left? All right, so let me tell you about both. Let me go to this kind of structured data. So clearly, real data are not IID Gaussian noise, right? This is how I imagine real data, some like pictures, some actual people. So some of you probably have seen those particular pictures already, and those who did actually know that these are actually not real data. These are not real people. These are in fact outputs of a generative neural network generated by starting with a random noise and getting to that. So that's one of the kind of successes of deep learning. And we took an inspiration in that to actually think how to go beyond the assumption of the Gaussian IID data. And the way we did that, you know, here is just a little schema how these generative networks actually work. So generative networks are neural networks as the one as I showed you, and instead of having typically a single output, they actually have as many outputs as is the number of pixels in the image. And typically they start from some latent space into which you feed just Gaussian IID noise, and then it goes through the network that corresponds to a function like that, where these weights f would be learned from data typically, and that then generates the data set x, data point x, that for instance looks like this dog. This is again a picture of a dog that is not a real picture, that is generated based on learning on similar pictures of animals or dogs. So okay, that's good to know. So maybe if we can actually have this, and here it's on the input, it's a Gaussian IID noise. So maybe that's enough for the replica methods to kind of go through and give us the calculation if we actually use data like that. So that was kind of our idea. And another way to think about the model that I'm going to mention is this one is kind of much closer to what I have seen that people think about in neuroscience, the fact that, well, any data, but in particular natural data actually lie on some low dimensional submanifold of the actual input space, which is illustrated here. If this is a picture of a horse and this is a picture of a boat, and if I took just a random point in that space, it would not correspond to a picture. So this set of pictures is this lower, much lower dimensional manifold. And the dimension of the manifold, if I go back here, would kind of correspond to the inputs to the generative network, and then the output, that's the number of pixels. So combining kind of this idea of the manifolds and data lying on a manifold and the generative network, we thought, okay, and maybe simple model for data that would be more realistic and goes beyond the Gaussian IID data would look like that. We take now the input C that is random IID Gaussian, but then we take some matrix F that we would like to be as generic as possible. And that actually produces the data X. And for this data X, we are now trying to get the learning curve and answer the questions. What's the best possible test error? And is it computationally efficiently achievable? And that actually turns out possible. And that turns out possible thanks to a property that, okay, when we realized that, we were very surprised and called it some kind of a Gaussian equivalence property. And that is the following, actually kind of unwrapping the replica method for a disorder that has this form. At first, it looked very complicated to us. But then we realized that if we actually want just the learning curve of a single layer neural network, then using data that are generated like that is exactly equivalent in terms of the shape of the learning curve to using data that actually do not have this nonlinearity phi, but has just some multiplication by a constant and the product here, and then adds a bit of noise and adds some identity. So this is something that, you know, later on we formalized partially, and yet later on colleagues in Harvard actually proved formally that this Gaussian equivalence indeed holds in this setting and gives the exact solution for the learning curve for data that look like that. And quite interestingly, kind of now I introduced this hidden manifold model, but mathematically completely equivalently, you can see the same equations as actually analyzing the learning with random features. If that is also related to kernel learning. So if you don't know what that is, never mind, but just for those who do, that's exactly mathematically equivalent. And analyzing that, we can end up with learning curves that look like this, that for instance have this behavior that have been observed in deep learning of this double descent that actually at the interpolation threshold or at linear separability for the classification threshold, the test error is actually large, bad, but then when we over-parameterize more and more, it actually gets good again. And as this dimension P goes to infinity, it actually converges to the kernel limit. So this is a clear solvable case where we can put these properties into closed scalar equations. That has been done before for the regression, but for the classification, no. And that was our paper who kind of brought that generalization of those formulas and this kind of more general analytical solution for these double descent curves in line. But so again, it's follow-up papers where we kind of were going after this idea, after this Gaussian equivalence theorem, kind of being at first surprised and then exploring the fact that even non-Gaussian structured data actually in terms of the learning curve often behave as if the data were Gaussian. And it's not always true. And the kind of task of figuring out when exactly it is true is still ongoing. So here are some of our papers in that direction. And I just want to show you one picture from the last one, which is actually about the case with random labels. So that's the case of storage capacity that kind of the old timers are more familiar with maybe than the teacher-student kind of setting. And here I took the paper of Gardner and Derrida about the storage capacity with their figure 2, where they actually compute this threshold 2 that is, you know, that had universality for properties that was known from before from the work of Cover. But then they plot here, in a sense, the ground state, the smallest number of patterns that one can get unsatisfied. And what we realized is actually that even this curve corresponding to the ground state has a very, very strong universality property, which is illustrated in this picture, where we kind of all the points are actually real data sets, usually after some transform, say scattering transform or random features, or maybe Gaussian mixtures. So those are all the points in different settings for different losses. And the lines, those are the curves coming up from the replica theory for the Gaussian data. And you see that they are always, the points are always lying on the lines. So this for me is kind of a redemption of this Gardner-Derrida work for the Gaussian data, because I often, in this line of work, I often heard the criticism, okay, this is nice what you do, but it only concerns Gaussian data. I was like, yeah, you're right. But no, it doesn't. There is a huge universality class. And for these random labels, it really is huge. That very large set of data will have exactly the same kind of Gardner capacity ground state energy as the Gaussian data. So this is kind of like surprising to me, at least when we found about it. And in the last few minutes, I want to go to the third side about, so far I was a bit putting hidden units because I talked about the random features, but then I was not learning the first layer. I was telling you about the phase retrieval over parametrize. That was a bit an exception where I was actually learning the first layer. But let's talk about it a bit more systematically. What happens to this line of work, to this whole approach, when we actually want to put in hidden layers? So first, an easy case. What if I put in just order 1 hidden neurons, and I keep that high dimension limit when the dimension and the number of samples go to infinity with fixed ratio? So that's a case that's called the committee machine, and that actually was solved already in the 90s. The kind of key paper for the batch learning is the paper by Schwarze in 92. And a bit similarly to the generalized linear model, we kind of proved that those formulas were indeed correct and put it in connection with the approximate message passing algorithm and its performance. And already in this case of very few hidden units, we have interesting things. Again, one that has been known in the statistical physics literature about the specialization phase transition, that there actually is a threshold in terms of the sample complexity, below which, even though the teacher had several hidden units and the student has a matching number of hidden units because there's the base optimal kind of student, the performance is not better than if we were using just linear regression, just no hidden units. So that's just statistically impossible to do better from few samples. And when the sample complexity is above the threshold, then it is possible. Then truly, the student realizes that it is better to specialize the two neurons in this case and actually learn the two directions of the teacher. So that's one property. And another one is that when then this K, the number of hidden units, is actually much larger than 1, but after N and D went to infinity, then there is again this computationally hard phase that starts to open, and that actually is pretty large. And I told you already before that this will have consequences and hurdles for the gradient descent. So we have to expect something like that also when we have hidden units. Okay, but are we satisfied with just few, like 5 hidden units? No, that's not what the state-of-the-art architectures look like. Those have many hidden units. So here in blue, I actually give you kind of 3 propositions of how to take the thermodynamic limit, including number of hidden units, that is large, but not too large. Because if it is too large, then, I mean, there is a pretty established and active line of work that the neural networks actually are equivalent to kernels. And in that context, many things are understood. But I want to be in a regime where that's actually not the case, where I can do some non-trivial statistical mechanics of truly feature learning. And so let me go through the limits. So the first one, I would take number of outputs. I also play with the number of outputs, which will be n. And I will take the usual, just one output or the one outputs, and I will take number of samples that is proportional to the dimension, and the width will also be proportional to the dimension. So that is kind of one limit that to me makes sense. Another one would be the same, but the number of samples is actually proportional to the square of the dimension. Why? Well, because the teacher uses these square numbers to kind of produce the labels, so maybe that's a more kind of meaningful scaling. And yet another proper scaling is that now if the output is actually also extensive, and I only have linearly many samples. So all these make sense to me. What can we say about them? So that's a very recent work that we put on the archive just a few days ago, where we actually figure out what's going on in the limit A. And I was excited about that, but the result is kind of boring in a sense, because we do have an explicit formula for what's the optimal error there, but it is the same error that can be achieved just by regularized ridge regression. So what this says is that in this limit, when the output is scalar and I only have linearly many samples, and otherwise everything else is just extensive in the dimension, everything else scales linearly with the dimension, in this limit, depth is not needed. Information theoretically, I cannot do better than regularized ridge regression. So from that point of view, it's a bit of a boring limit. So what about the other one, where I actually take quadratically many samples? Well, in the same paper, we show numerically that that's indeed where things get interesting, where you start to be able to learn the teacher function exactly. So you go away from what ridge regression or canal ridge regression is able to do, non-trivially so. But the drawback there is that nobody actually knows how to analyze that limit. Not even non-rigorously using the replica method or any kind of other approximate statistical physics method that would actually capture this behavior. So to me, that's kind of one of the simple kind of to state. It's not even about a complicated architecture or some complicated setting, but that's kind of the challenge. Why methodologically what we do, why does it really fail? What are the correlations here that the replica method is kind of not able to decouple? To me, that's a very kind of important and challenging question. And that brings me to the third limit, which is the one where I take an extensive output and linearly many samples. That one is also hard for the same reason as the previous one. But that one is kind of maybe interesting for, that's my last slide, for the kind of neuroscience community, because it's related to a problem about the Hopfield network. It's a problem that we actually formulated in a paper a few years back in collaboration with Nicolas Brunel, where we took the Hopfield network, the usual one that stores extensively many patterns, and we asked the question whether you can retrieve the patterns, but differently than one does usually, because usually one needs a correlation with one of the patterns to retrieve it. And we said no correlation with any of the patterns allowed. Just from the coupling matrix, can you retrieve the patterns? That's a question that, okay, we haven't seen stated this way in the literature before. And we looked at it algorithmically when the number of patterns stored is very small. In this case, we were able to solve it and we have some nice results on that. But when you actually store extensively many patterns, this is a problem that we call the extensive rank matrix factorization in signal processing. It's also equivalent to a problem that is called addiction learning. And that, again, is a problem that we don't know how to solve. We don't know how to compute the exact free energy using the replica method. And this is kind of explained and in a technical manner in this paper. And there is a very recent paper by Mark Mazarin, a student of his, where he kind of shows that information theoretically is possible, but the algorithm to do so is actually not efficient. So I just want to bring this to your attention. There is something mathematically very non-trivial in order to be able to crack either the limit B or C. And that's the whole talk. This is just, again, kind of this triangle that I like to keep in my mind. So I just leave it here for you to perhaps keep it in your mind. And I want to thank my current group that is working very closely with Laurent Chakala's group, that's the IDEFIX And this is our two groups together at EPFL.